So, to retrace our steps, let us look at one of the solutions of the algebraic homogeneous equation. Let us say we pick Sk. Some k which is less than capital N, of course. So, what do we do with this Sk? We know that it is a solution to the algebraic equation, and hence if we go back to the factorized form of the solution of the homogeneous differential equation, namely e to the st summation k equals 0 to n. Well, let me not call this Sk, there is confusion can be caused. I will call it S n. Let us say I call it S n. So, this was our factorized form of the solution, e to the power st times k equals 0 to capital N a k s to the k. This was the factorized form. Now, if S n is a solution for the algebraic equation, then if I put S n over here, that is if I subscript this S by n, so that I have chosen S to be the nth root of the algebraic equation, then we already know that the right side factor, the polynomial factor in this solution of the homogeneous equation will become equal to 0, and hence this entire expression will become equal to 0. So, if I write n in both these places, that is if I use S equal to S n, then the expression indeed solves the homogeneous differential equation. Thus, after I have put S equal to S n in this entire expression, e to the power S n t times summation k equals 0 to capital N a k S n to the k, this entire thing evaluates to 0, because as I said the polynomial factor evaluates to 0. Thus, we seem to have found a solution to the differential equation. The original differential equation, if we recall, we are taking now our second step backwards. We have moved from the homogeneous algebraic equation and reached the homogeneous differential equation, the solution of the homogeneous differential equation. Now, we want to go further, but to recall where we are exactly, let us now see that when you have the homogeneous differential equation as a k dk y t to dt k, k equals 0 to n, this was our homogeneous differential equation. When the right side is set to 0, then we know that if you use y t equals e to the power s n t, then this equation is indeed solved. So, e to the power s n t is a solution. For the homogeneous equation. That is nice. We managed to solve something at least after having gone round and round, we have solved something at least. But this that we have solved, this part that we have solved has a lot of ramifications. What we have already done will take us another 15 minutes at least to understand the implications of it. Now, from what we have written over here, the first thing I can say is that I just chose S n as one of the capital N roots of the polynomial algebraic equation. If e to the power S n t is a solution for this differential equation, for the homogeneous differential equation, then I can make the following remarks immediately, and each of these remarks will turn out to be self evident or will require very little explanation. First, if e to the power S n t solves the homogeneous equation, then inevitably so will e to the power S 1 t, e to the power S 2 t and e to the power S subscript capital N t. All these will solve the homogeneous equation. So, we did not get one solution for the homogeneous equation like we wanted, we already got capital N solutions, and fortunately or unfortunately the story does not even end there, it gets much bigger than that, as we will see in a little while. We have n solutions for the homogeneous differential equation. Let us choose any one of them and study further. Consider the solution e to the power S small n t. This is one of those solutions. Small n takes some value between 0 and between 1 and capital N. If this is a solution, let us see what happens if you use a scaled version of this same function. Scale it by any complex constant say C to get C times e to the power S n t. Substitute this C e to the power S n t in the homogeneous differential equation. What do you expect you will get? This is what we have, and what is this equal to? Every time you differentiate a function that is scaled by a constant, the constant factors out of the differentiation. We know that differentiation is linear with respect to scaling as well as superposition. Furthermore, we just have a sum of these terms, and C is going to be a common factor in all these terms. So, we will simply get this C times k equals 0 to n a k d k e to the power S n t by d t to the k, which is C times this same differential equation we had earlier, for which we know that e to the S n t is a solution. So, this whole thing is just equal to 0. What does that mean? That means that not only are e to the power s n t, n equals 1, 2 up to n solutions for the homogeneous equation. So are, or rather also, c times e to the power s n t are solutions. And remember, we can put any value for c. C is a constant, but it is what we call an arbitrary constant. C is an arbitrary constant. Now, there is no room to get confused. What do we mean by saying it is arbitrary and constant at the same time? We simply mean, when we say it is a constant, we mean that it is not a function of time. It's once you set a number for it, a value for it, it stays the same number irrespective of what time it is. On the other hand, you can choose any number you like. So, it is not a function of time, in that sense it is a constant, and it can be any number you like, therefore it is arbitrary, it is an arbitrary constant. You can choose c to be any number from plus infinity to minus infinity if you want it to be real. You could even choose any number on the complex plane if you want it to be complex. For every one of those choices of c, you will have c e to the power s n t as a solution for the homogeneous equation. So, that means that we do not have just one solution for the homogeneous differential equation. No, we do not have just n solutions, capital N solutions, as we thought a little while ago for the differential equation. No, we have now an infinite number of solutions for the homogeneous differential equation. In fact, if you pick each one of these sk's or SNs, each one of the roots of the homogeneous algebraic equation, associated with each of those roots, you will have an infinite number of solutions, which you can generate by changing the value of c over and over again on the complex plane. So, in fact, you can of course loosely say that you have an infinite times capital N number of solutions. Infinity times capital N is still infinity. So, anyway we can say that there are an infinite number of solutions. Okay. So, we have all these solutions. Now, the matter does not even end here, and that is what is so surprising. Let me now make the final most general statement that will truly define the scope of the solutions of the homogeneous differential equation. In order to say this, I will first denote by phi t any function that solves the homogeneous differential equation. So, we already know that there are a multitude of these phi t's. I can have phi 1 t, I can have phi 2 t, I can have phi 3 t, each one different from the other. For example, I can choose phi 1 t equals 2 e to the power s 1 t. I can choose phi 2 t equals pi times e to the power s 4 t. Pi is a constant, arbitrary constant, so I chose it to be pi. then 2 is another constant, and here I have chosen the root S1 of the algebraic equation, here I have chosen the root S4 of the algebraic equation. So, in spite of all this variability and all this freedom I have, phi 1 t solves the homogeneous equation, phi 2 t also solves the homogeneous equation. So, I have just taken two different solutions of the homogeneous equation, since I already know at this stage of the argument that there are lots of solutions. I can choose 2 of them, I can choose 100 of them very easily. Now, what we were waiting for, we can see very demonstrably, very easily that phi 1 t plus phi 2 t also is a solution for the homogeneous equation. Remember that phi 1 t and phi 2 t are certainly distinct functions. They do not look the same, they are not the same function. And furthermore, phi 1 t plus phi 2 t is different from both phi 1 t and phi 2 t. It is non trivially distinct from both. And yet, this new creature, that is phi 1 t plus phi 2 t, also turns out to be a solution for the homogeneous differential equation. We can demonstrate this very easily. We have not done this yet. Let us just do it. Let us take, well, what are our input facts for our argument? The facts are that we have this, since phi 1 t is a solution by assumption for the differential equation, this equals 0. Likewise, this is also equal to 0, because phi 2 t is also a solution. Now, let us see what happens if we apply phi 1 t and phi 2 t simultaneously, that is, add them, superpose them, and consider them to be a solution for the equation. Let us see if it is still a solution. Very obviously it is, because what we have on hand is k equals 0 to n a k d k phi 1 t plus phi 2 t by dt to the k. This is what we want to examine. Is this a solution? We suspect it is, and we want to prove this. What is this equal to? This is equal to the summation This is what it is. So, each term has split into two terms. What we will now do in the summation is to split the entire summation into two summations. Now, we already know that phi 1 and phi 2 are solutions for the homogeneous equation. In short, each of these two summations is individually 0. This is individually 0 and this is individually 0. So, the entire expression is 0. This proves that if phi 1 and phi 2 are taken out of the set of homogeneous solutions, then phi 1 plus phi 2 is also a member of the class of homogeneous solutions for the homogeneous equation. You can in fact easily establish a slightly more general result, that is that if phi 1 and phi 2 are solutions for the homogeneous equation, then in general C 1 phi 1 t plus C 2 phi 2 t solves the homogeneous equation. That is very evident, because all that will happen can be demonstrated in the expressions we have already written over here. All that will happen is we will have dk by dt k of C 1 phi 1 plus C 2 phi 2, which will split into two derivatives, a k times dk C 1 phi 1 by dt k plus dk C 2 phi 2 by dt k. By the linearity, the homogeneity of the differential operator, we would get a k times C 1 dk phi 1 by dt plus a k times C 2 dk phi 2 by dt. Then we could split it into two summations, as we already have done, and each such summation would be 0, because C 1 would be a common factor for all the terms in the first summation, C 2 would be a common factor for all the terms in the second summation. The whole thing still comes to 0. Now, this brings us to a realization of the vastness of the collection of solutions, of the family of solutions for a homogeneous differential equation. We do not have one solution, we do not have two solutions, we have an infinite number of solutions, a huge infinite number of solutions for the homogeneous differential equation. That is the state of the story up to now. Now, we want to add a few refinements to our understanding. We want to see whether we can somehow understand the relationship between the different solutions. It is not the case that though there are an infinite number of solutions, all the solutions are arbitrarily related to each other, or are arbitrarily different from each other. They are all related to each other in a very nice manner. And in order to show you how they are related to each other, I will have to invoke the notion of a vector space, the vector space of solutions of the homogeneous equation. The vector space of solutions to the homogeneous equation. Well, if you do not know what is a vector space, do not worry too much about what I am about to say. If you do, you will be happy to understand that this set of solutions to the homogeneous equation constitute a vector space. A vector space resembles our 3-dimensional physical space. An n-dimensional vector space has n orthogonal axes. Or can be made to have each axis is identified with a so called basis function, which you would normally call a unit vector in that direction. By a basis vector. An arbitrary vector in the space that is to say an arbitrary point in the space may be expressed as a linear combination of the basis vectors. So, I have just numbered the points. An arbitrary vector in the vector space, which is to say an arbitrary point in the space, each point in the vector space is a vector in its own right, may be expressed as a linear combination of the basis vectors, where, or let us make a new point, the weights of the linear combination are called the coordinates of that point. Or of that vector. Okay. So, now what is all this talk of vector space got to do with the set of solutions of the homogeneous equation? What it has got to do is just this: we can organize all these huge number of solutions into the structure of a vector space simply as follows. Let there be an n dimensional vector space and the n basis vectors or the n basis functions be chosen to be e to the s1 t, e to the s2 t and so on. So, if we choose these as the basis vectors, then clearly we can see that not only are each of these basis vectors solutions for the homogeneous equation, but any linear combination of these basis vectors is a point that lies in the same vector space on the one hand, and from our knowledge of whatever we have just learnt in the last half hour, is also a solution for the differential equation, for the homogeneous differential equation. Then in short we can say that each basis vector solves the homogeneous equation, fine. Each basis vector solves the homogeneous equation, and by what we have found, each point, by which I mean vector, in the space which has e to the S1t on to e to the S n t as a basis, may be expressed as a linear combination of them, and hence is also a solution. So, we have constructed a vector space whose basis vectors are the fundamental solutions, the most basic solutions we got, e to the S1t, e to the S2t on up to e to the Snt. And we have found that every point in the vector space which has this set of vectors as a basis will also be a solution for the same homogeneous equation. So, the concluding remark, the enlightening remark is that thus the set of all solutions for the homogeneous equation is a vector space in which e to the power s k t, k equals 1 to n, can serve as a basis. This gives us a good picture of the manner in which the solutions of the homogeneous differential equation are organized relative to each other. This is also probably the last remark that we can make about the homogeneous solution alone. We are now therefore in a position to take the next step forward, solving the non-homogeneous equation. What was the non-homogeneous differential equation? This was the original differential equation, where we had a non-zero forcing function x t. So, let us write it out. this is going to be a different kind of game altogether, because we do not have 0 on the right side. Because we do not have 0 on the right side, there are lots of things we did earlier which we cannot do now. Our approach in trying to understand what sort of functions can be substituted for y t that will ensure that the left hand side evaluates to x t for every instant of time is therefore going to be governed by other considerations. We want to know how we can do this. Before we even begin, in order to simplify the exercise, we will have to make certain assumptions, some constraining assumptions which will allow us to proceed. Probably we can relax these assumptions later, but at the initial stage when we want to get an understanding, let us constrain our forcing function to be one of a few different kinds of possible functions. To seek a solution, the non-homogeneous differential equation we will abbreviate to NHE, the non-homogeneous equation. To seek a solution for the NHE, we have to consider only very simple forms of x t. We confine simple cases for x t. What are these simple cases? What constitutes a simple case? The answer is the following. We want to consider such x t's for which y t will be of the same form as x t. We want to consider such functions x t for which y t can take the same form as x t. Further, we want such functions where the derivatives of y t have the same form as y t. So, this what we have just written we shall call the first constraint. Moving on to write the second constraint, we will say we would also like to have such a y t that has derivatives of the same form as itself. So, two constraints, x t and y t should be of the same form, y t and its derivatives must be of the same form. Now, what sort of functions satisfy these constraints? इतना जल्दी हो गया?